June 6, 1944, 0730 hours, Omaha Beach, Normandy. A private named Ingram Lambert crawls through the surf toward the seawall, dragging a 5-foot steel tube behind him. German machine guns rake the sand. Men die around him. Lambert reaches the barbed wire blocking the beach exit, shoves the tube underneath and pulls the friction igniter. Nothing happens. The fuse has failed. Before he can fix it, a burst of fire cuts him down. A lieutenant crawls to the same spot, repairs the igniter and detonates the charge. The wire shreds apart. The first man through the gap is shot dead. Then Brigadier General Norman Cotter pushed men through the gap, then went through himself, leading by example. His men follow. That steel tube, invented by a British officer in India 32 years earlier, had just cracked open the Atlantic wall. The Bangalore Torpedo looked like plumbing, 5 feet of thin steel pipe just over 2 inches in diameter. Soldiers carried it in sections that screwed together. The whole assembly weighed 13 pounds per section and contained 9 pounds of high explosive. Push it under an obstacle, light the fuse, run. The blast would shred barbed wire, detonate mines, and clear a path 3 to 4 meters wide. The method of delivery was the problem. Someone had to crawl within arm's length of enemy positions, assemble the device while under fire, and hope the fuse worked before a bullet found them. Gap assault teams using Bangalore's on D-Day suffered nearly 50% casualties, according to historian John McManus. The weapon worked. The cost was measured in bodies. German defensive doctrine on the Atlantic Wall centered on stopping invaders at the waterline. Field Marshal Erwin Rommel, appointed to inspect coastal defences in late 1943, understood that Allied air superiority would prevent meaningful counterattack once troops established a beachhead. The battle would be won or lost on the beaches themselves. Rommel ordered construction of elaborate obstacle belts across every potential landing site. Hedgehogs, welded steel beams arranged in crossed patterns, would rip the bottoms from landing craft. Belgian gates, massive steel frames 10 feet high, would block vehicle passage. Tetrahedra, concrete pyramids with steel spikes, would impale boats at high tide. These obstacles worked seaward, stopping the assault before it reached shore. But Rommel also understood that any troops who survived the obstacle belt and reached the beach would face a second barrier. Wire, miles of it. Barbed wire in multiple rows, concertina wire in coiled spirals, double apron entanglements with stakes and crisscrossed strands. This wire protected the beach exits, the draws and ravines that vehicles needed to move inland. German doctrine positioned machine gun nests to cover every meter of wire with interlocking fields of fire. Any soldier attempting to cut through with hand tools would be exposed for minutes under direct observation. The wire did not need to stop attackers permanently. It needed to hold them in the killing zone long enough for bullets to finish the work. Allied planners studied aerial reconnaissance photographs and understood exactly what awaited them. By June 1944, over 500,000 beach obstacles were in place along the invasion coast. The wire obstacles were positioned with geometric precision, each strand placed to maximize exposure time for any soldier attempting to breach them. German engineers had studied the failures of the First World War and designed entanglements specifically to defeat the cutting tools and explosive charges that had eventually broken through static defenses. Double apron fences used diagonal wires that sprang back when cut, requiring multiple cuts to create even a narrow gap. Concertina coils were staked at intervals that prevented soldiers from simply lifting and crawling under. Every improvement in breach technique had been answered by an improvement in defensive wire. The obstacle problem that created the Bangalore predates the First World War. Captain R. L. McClintock of the Royal Engineers invented it in 1912 while stationed with the Madras sappers and miners in Bangalore, India. His purpose was not trench warfare, which had not yet begun. McClintock needed to clear booby traps and barricades left over from the Boer War and the Russo-Japanese War, which continued killing colonial troops and civilians years after those conflicts ended. Previous methods required sappers to approach obstacles directly, exposing themselves to hidden explosives or enemy fire while working with hand tools. McClintock wanted standoff capability, a way to destroy obstacles from a protected position. The solution was elegant. Identical steel tubes that screwed together using threaded connecting sleeves. One or more sections contained explosive. Empty sections provided length to reach obstacles from cover. A smooth nose cone prevented snagging as sappers pushed the assembly forward. The genius was modularity. A sapper could assemble exactly the length needed for the obstacle at hand, no more and no less. The first prototypes were built cheaply and fast from locally available materials. The British Army formally adopted the design in 1914, just as the Great War transformed its intended purpose entirely. The Western Front's elaborate wire entanglements made the Bangalore essential. Defensive positions featured wire belts sometimes hundreds of yards deep, layered in multiple rows with overlapping coverage. Previously, sappers had to crawl forward with wire cutters, exposed to enemy fire for extended periods while snipping strand by strand. Artillery could destroy wire, but bombardments also cratered the ground, creating obstacles of their own and alerting defenders to imminent attack. The Bangalore allowed assault troops to breach wire quickly and quietly, pushing tubes from shell holes or trenches, then detonating remotely with time fuses. By the war's end, Bangalores had become standard equipment for any assault on fortified positions. The technical specifications evolved across 3 decades of warfare. The American M1A1 variant, standardized in 1943 and mass-produced through 1944, became the definitive configuration for the Second World War. Each individual section measured 5 feet long and 2.125 inches in diameter. Total weight was 13 pounds, of which 9 pounds was 80-20 amatol, a mixture of 80% ammonium nitrate and 20% TNT, with 4-inch TNT boosters at each end. The boosters ensured reliable detonation across the full length of the explosive column. Spring clip-equipped sleeves replaced the original threaded connections for faster combat assembly. A soldier with numb fingers from cold water could connect sections by feel alone, snapping clips into place without the fine motor control threading required. Up to 10 sections could connect, reaching approximately 50 feet in total length. Packaging came in wooden crates containing 10 torpedo sections, 10 connecting sleeves and 1 nose sleeve, with total crate weight of 176 pounds. The blast effect was lateral rather than cratering. Overpressure and casing fragmentation shredded wire obstacles outward in both directions, creating a gap for infantry passage rather than digging a hole. This made the weapon effective against barbed wire, concertina wire and double apron entanglements, but not against heavy steel structures. Belgian gates required shaped charges or vehicle-mounted demolition. The Bangalore's purpose was wire first, sometimes heavy undergrowth, anything you could reach by pushing the charge forward. Americans produced approximately 3,255,000 torpedo sections during the war, according to Ordnance Department records. This staggering number reflects anticipated demand for the desperate work of breaching defended positions. British Commonwealth forces adapted specifications to available materials. At the Battle of Bardia in January 1941, Australian sappers carried 12-foot pipes filled with ammonal rather than the American amatol configuration. Now, before we see how this performed on D-Day, if you are enjoying this deep dive into British engineering, hit subscribe. It takes a second, costs nothing, and helps the channel grow. Alright, back to Normandy. By June 1944, British and American approaches to obstacle clearance had diverged dramatically. The British had learned from catastrophe. At the 1942 Dieppe raid, sappers suffered 85% casualties, the worst of any unit type. Of 71 assault sappers who landed, only 10 returned to England. Of 98 demolition team sappers, only 8 came back. 27 died on the beaches alone. Canadian and British commanders witnessed engineers cut down in rows as they attempted to place charges against seawall obstacles. This slaughter prompted aggressive mechanization. Major General Percy Hobart developed specialized Churchill tanks, including the AVRE, the Armoured Vehicle Royal Engineers, with its devastating 290mm petard mortar that fired 40-pound charges capable of destroying concrete bunkers. Sherman Crab flail tanks rotated chain flails, powered by auxiliary engines to detonate mines and tear through wire. The Crocodile flame tank could incinerate defensive positions from 120 yards. By D-Day, British planning aimed to reduce reliance on man-portable Bangalores, because Dieppe had proved what infantry delivered explosives cost in lives. Armour would lead wherever possible. The Americans retained the M1A1 as standard engineer equipment. Combat engineers from the 116th and 16th Infantry Regiments, the 2nd and 5th Ranger Battalions, and the 121st and 146th Engineer Combat Battalions carried Bangalores as primary breach devices. American commanders observed British mechanization, but chose a different path. They believed infantry portable explosives offered flexibility that vehicles could not match. A man with a Bangalore could reach places tanks could not go. Training for D-Day assault engineers was brutal and repetitive. At Slapton Sands in Devon, selected for its resemblance to Normandy beach conditions, soldiers practiced the Bangalore drill hundreds of times, check for tripwires and booby traps, connect required sections using connecting sleeves, push the assembled torpedo through or under the obstacle, insert and secure the blasting cap with fuse, retreat to minimum safe distance of approximately 20 yards prone behind the device, detonate and immediately assault through the cleared path. The entire sequence had to become automatic because conscious thought would be impossible under fire. Engineers participating in Exercise Fabius and the Duck exercises in February and March 1944 rehearsed until their hands could assemble torpedoes in darkness, in cold water, with simulated casualties screaming around them. No training could fully replicate the chaos of actual opposed landings. Tactics and procedures were often worked out from scratch in real time on D-Day itself. The critical distinction on D-Day was timing. The invasion planners chose low-tide landing to expose German beach obstacles, allowing engineers to destroy them before tanks arrived. But the tide rose approximately 1 foot every 10 to 15 minutes after H-hour. Engineers had only 20 to 30 minutes to work before water covered the obstacles. The tanks could not land until the work was done. When 27 of 29 DD tanks from the 741st Tank Battalion sank in rough seas before reaching Omaha, infantry engineers became the only option. And when those men reached the seawall shingle, exhausted from the crossing and terrified by the slaughter around them, they faced multiple rows of barbed wire, concertina wire, and double apron entanglements blocking every beach exit, wire that vehicles could not yet reach, wire covered by machine gun fire from fortified positions above, wire that only the Bangalore could clear. The combat accounts from Omaha reveal the weapon's desperate importance. At Dog White Sector around 0750 hours, General Cota found pinned troops at the seawall and ordered soldiers to position a Bangalore under the wire. After Private Lambert's death and Lieutenant Stanley Schwartz's repair of the failed igniter, the detonation blew a gap. Cota went through first. His soldiers followed. This single breach, opened by British engineering and American courage, became one of the first penetrations of the Atlantic Wall defences on Omaha Beach. At the same beach sector around 0810 hours, the 5th Ranger Battalion blew 4 gaps in the wire with Bangalores, then crossed the beach flat at the double. Heavy smoke from burning grass, ignited by naval gunfire, provided concealment as men climbed the bluffs using paths their engineers had died to create. A soldier from Company C, 116th Infantry, dropped his body onto remaining wire strands after a partial gap was blown, forming a human bridge for his comrades to cross. Another soldier preparing to place a second torpedo was shot down while positioning it. A lieutenant reached the device and lit the fuse, completing the breach at the cost of 2 men's lives. At the Veerville Draw, the crucial vehicle exit from Omaha Beach, engineers used Bangalores to clear protective barbed wire around anti-tank walls before placing TNT charges against the structures themselves. By late afternoon, both walls were destroyed, opening the first usable vehicle exit on the beach. Every vehicle that moved inland that evening passed through gaps that Bangalore torpedoes had helped create. The mathematics of this work approached certain death. Naval combat demolition units at Omaha recorded 31 killed and 60 wounded of 175 men, a 52% casualty rate representing the bloodiest single day in naval special warfare history. The danger was inherent to the task. Soldiers had to advance within small arms range of enemy positions. Assembly required connecting multiple 13-pound sections while exposed, potentially taking 5 to 10 minutes under fire. German defenders specifically targeted demolition teams, recognizing their threat to defensive integrity. NCDU-23, known as Vetter's Vandals, was completely annihilated when a German shell struck their rubber boat, carrying 300 pounds of explosives. The British approach on Gold, Juno and Sword beaches showed the alternative. Hobart's funnies led the assault. Sherman crabs flailed paths through minefields while protected by armour. A VRS blasted concrete with petard mortars. The casualty rates among British engineers, while still significant, were substantially lower than their American counterparts on Omaha. The lesson was clear. Mechanization saved lives. But mechanization required the right equipment to be available at the right time. When tanks sank or bogged down, when the tide closed the window, when obstacles appeared where planners had not expected them, infantry with Bangalores remained the only solution. The weapon's post-war service confirms its irreplaceable utility. American forces used it throughout the Korean War for breaching Chinese defensive positions. In Vietnam, both American troops and Viet Cong employed Bangalores, with the enemy manufacturing local versions from available materials using captured examples as templates. Israeli forces cleared paths through Syrian minefields during the 1973 Yom Kippur War, where the weapon proved decisive in breaking through fortified positions on the Golan Heights. US combat engineers employed them in Afghanistan and Iraq for clearing IED-laden barriers and Taliban supply positions. The current American variant, the M1A3, uses aluminium construction and composition B4 explosive for improved performance and reduced weight. The British developed the L26A1 Advanced Performance Bangalore Torpedo through Chemring Energetics UK, featuring lightweight aluminium tubes, DPX-1 explosive, and quick turn threads designed for assembly when contaminated with mud or sand. The modern British version clears wider paths than McClintock's original, while remaining compatible with the fundamental concept he established over a century ago. Both nations continue improving the design because no alternative has proven superior for infantry portable obstacle breaching. Most remarkably, in late 2023, reporting showed US-supplied Bangalores being used by Ukrainian forces against Russian defensive belts. Over 113 years after Captain McClintock assembled his first prototype in India, British sappers' solution to colonial obstacles continues clearing paths through enemy defences in European combat. The comparison between British invention and American adoption reveals a pattern seen throughout military history. British engineers pioneered the concept. American industry mass-produced a standardized battlefield kit. The original Bangalore used threaded connections requiring multiple rotations to assemble each joint. American spring clips allowed faster assembly by cold, wet, or trembling hands. Britain pioneered mechanized alternatives through Hobart's innovations, reducing reliance on infantry-delivered explosives. America mass-produced the infantry version for situations where vehicles could not reach. Neither approach was wrong. Each served different circumstances, but the foundation remained British engineering, solving a problem in colonial India that would prove relevant across 3 centuries of warfare. Captain McClintock could not have imagined D-Day when he built those first prototypes for 9 rupees. He was solving an immediate problem with available materials, that his solution would blast gaps through Hitler's Atlantic Wall, clear paths through Korean minefields, enable Israeli breakthroughs in the Golan Heights, and support Ukrainian counteroffensives in 2023 speaks to something fundamental about good engineering. Simplicity endures. The Bangalore has no moving parts, nothing to break mechanically. It is steel tube filled with explosive, pushed forward by human beings who understand the odds are against them. The gap assault teams of Omaha Beach accepted near certain casualties and advanced anyway. General Kota did not merely order men through the gap his Bangalore had blown. He went first himself, understanding that some missions require leaders to share the risk their tools cannot eliminate. The weapon enabled the courage. The courage made the weapon effective. Over 113 years of continuous service, one of the longest operational lifespans of any breaching weapon in military history. From the Madras sappers' workshops to the beaches of Normandy to the trenches of Ukraine, British engineering has cleared the path. That is the legacy of Captain McClintock's 9 rupee prototype, still proving its worth on battlefields he could never have imagined.